Hey guys, welcome to the last video on carbocation rearrangements. This is going to be a subset of the alkyl shift I showed you guys before. All right, it's called the ring expansion. Now don't worry, if you're still a little shaky on carbocations, there's plenty of ways you guys can practice, and also a lot of the alkene reactions will be involving carbocations, and so you'll have plenty of practice on your workshop quizzes, recitation, and from old exams and pre-class quizzes. And also I have my review problem set up shortly, okay? And so you'll still have plenty of ways to practice them if you're a little shaky. And so let's go over the ring expansion. Now this one trips up a lot of people, but it doesn't have to if you just follow it a few simple tricks of getting through it, okay? So I use the same exact reaction that we've seen before. And so this is going to start out exactly in terms of arrows how we've seen it happen before. The double bond attacks the hydrogen, and this bond breaks. So again, redraw everything exactly the same. Redraw what you know hasn't changed. Okay, actually, let's make this hydrogen over here and the chlorine, let's make them blue. Okay, so we added our hydrogen. We're going to add it here, correct? Because the carbocation we want to form is the more stable one. So between the left and right carbon, the left is the secondary, the right is a primary. Secondary is going to be more stable than the primary, okay? And so remember, we still have our chlorine over here. And so what happens next? Now remember, whenever you have a carbocation, don't immediately go for the chlorine attacking the carbocation. Always look to see if you can shift, okay? Remember, so if you can shift to form a more stable carbocation, you will. You'll never shift to form a carbocation that's the exact same in terms of substitution as in secondary to secondary, and you'll never shift to something that's less stable, like a secondary to a primary, okay? And so let's see if we can, so how can we shift in this case? Now, the ring expansion is a very specific type of shift, okay? It only happens, the concept of it is that a unstable ring, which four-membered rings are usually kind of unstable, or like three-membered rings, will open up and become larger rings, like 5- and 6-membered rings, which are more stable, okay? So it's going to form a more stable ring if we do this, okay? And the whole molecule will be much more stable in the process. And so how exactly are we going to do this? Well, the first step when doing a ring expansion is number your carbons. Please, please, please number your carbons. A lot of people make the mistake of not numbering them, and it's going to trip you up. So start from any carbon you want. I like to start them off the ring personally. Doesn't matter, whatever your preference is. So I'm going to number them 1, 2, 3, 4, 5, 6. Okay? Actually, let me just move the numbers to the outside just to give myself some room. Okay? And what is going to happen is we're going to, same concept as any of the shifts before. Your arrow has to start at a bond. And what we want to do is open this ring up to make it either a 5 or 6 member ring. Okay? And so the way we're going to do this is we're going to take this bond over here, that one. You could take this bond. They're the same, it doesn't matter. And we're going to expand it. We're going to open it up. So the way we're going to do that, we're just going to start from here, disconnect it from carbon 3. Okay? You'll see why we're disconnecting it from carbon 3. And it's going to form, and it's going to shift to carbon 2. So I'm going to redraw it in the ugly way to help you guys better see it. Okay, here's our hydrogen still there. And renumber your carbons every time. So our 1, 2, 3, then we had our carbon 6, 5, and 4. And so before I show you guys the formal charge, let's see what we did. I disconnected it from carbon 3, but left it connected to carbon 4. And I simply shifted it. Let me see if I can try to draw it like a little shift for you guys. That was ugly. Right, and so I disconnected it from carbon 3, and what I did is I took this and I sort of moved it onto carbon 4. That was bad. Like this. That's just an ugly curve, but the representation is the same. All right. So I kept it attached to carbon 4, just removed it from 3 and put it to 2. And it has to go to the carbocation. It can't just form a bond with carbon 1, right? And you can see that we're only shifting at a distance of 1 carbon from 3 to 2, all right? And this is where numbering your carbons helps, right? And so since 3 lost a bond, it now has an incomplete octet. So it gets a positive charge. And so now we're going to redraw this in the nicer looking way. And so if we look, let's count the numbers of our ring. 2 right here, 3, 6, 5, 4. That's a total of five numbers, right? 2, 3, 6, 5, 4. 5 numbers. That means we have 5 members in our ring. Here, I'll even outline it for you guys. 1 bond, 2, 3, 4, 5. So now draw a 5-membered ring, okay? And renumber it. I like to draw only the ring before I draw anything else attached to it. Doesn't matter where you're starting your numbering, just keep it consistent. So in terms of where everything is, so do not make carbon 1 now part of the ring, because even though here it wasn't. All right, so started at carbon 2, 2, 3, 4, 5, 6. Carbon 3 had the positive charge, okay? And if we see off of carbon 2, we have carbon 1. So we're going to draw a bond. Let me just delete that. Off of carbon 2, we had carbon 1. And the blue hydrogen that we added in the first place is now there. Okay? And so I hope that helped you guys visualize the ring expansion. All right, and it's a good idea to get into the habit of maybe trying to draw the ugly way, like I did it over there, just so it can help you guys get used to the actual like movement of the bond. Okay, and then now at this point, the chlorine is going to come in and it's going to attack that carbocation. So we're going to be now left with this as our final answer. Right, that is the final answer of this of that question, that reaction. Now, just one quick thing. If we look at where our original carbocation was, it's on a secondary carbocation. If we look at where it ended up on another secondary carbocation. Now, the reason that this occurs, even though the carbocation is the same stability, is because of the overall stability of the molecule. 4-membered rings are not stable. There's a lot of ring strain for them. And so when we get to a 5-membered ring, we alleviate a lot of that strain. So it makes the overall expansion, the overall transition of the first carbocation molecule to the second is more stable now. It's much more favorable, and that's why it occurs, even though the substitution is the same. Okay, so just keep that in mind. And remember that these ring expansions only happen with carbocations. All of these shifts, only carbocations. When we get to the alkene reactions in the next videos, you'll see that there are some reactions that do not proceed through carbocations. So even if they're next to 4-membered rings, we will not be having these shifts. And we've been asked these questions in tests before, and a lot of people have been tripped up by doing a ring expansion when the reaction never went through a carbocation, and they will on purpose draw the ring to make it look exactly how you've seen it in all your workshops and all the quizzes, exactly set up like this, and a lot of people will get it wrong. All right, so remember, always number your carbons. That's the golden rule. Number your carbons, and that's a good habit to get into for a lot of the reactions you'll learn later on, especially in organic chemistry too, when you're dealing with larger molecules and much more complicated reactions. So if something in this video didn't make sense, please feel free to email me or go to the CLC for office hours. They're happy to help you guys, and I will see you in the next video.